Alright, so our next chapter that we're going to start here is going to deal with carboxylic acids and some related functional groups, namely esters and amides. Now we're going to start with some nomenclature as it pertains to carboxylic acids. We won't be covering ester or amide nomenclature in this course, but the carboxylic acid nomenclature is what we're going to do here. So the main new piece with carboxylic acid nomenclature, like any other functional group, is that we have a new ending, and the ending that we use is this one, oic acid. Otherwise, the nomenclature for carboxylic acids is extremely similar to what we learned for aldehydes. If you recall a similar aldehyde to this one, same number of carbons, 5 carbons, we would have called this pentanal. In addition to that, we wouldn't need to worry about the numbering because we would know that the aldehyde carbon was carbon 1. Same thing with carboxylic acids. The carboxylic acid carbonyl carbon is always carbon 1. And because of that, we don't need the number in the name. So our 5 carbon chain pentane, you can see our new ending there, becomes pentanoic acid. So other than that new ending, nomenclature for carboxylic acids is basically the same as aldehydes. So let's look at a little more complicated one. So a lot of the same things we've seen before. We number it starting at the carboxylic acid. So with 7 carbons, this is going to be a heptanoic acid. Now we also have the 2 alkenes to account for. So remember, that's going to go right here in the middle of the name. That AN, designating an alkane, becomes an EN, designating an alkene. So that's going to become hepta, and since there's 2 of them, 3,5-diene, and then the oic acid follows. We also need to name the substituents. 2-bromo, 5-hydroxy, 4-isopropyl, hepta 3,5-diene oic acid. Now, while that's most of it, we don't want to forget our stereochemistry. We have a chiral center at 2. We have an alkene at 3, and an alkene at 5. So our alkene at 5 is fairly straightforward. Hydrogen on one side is lower priority, carbon lower priority than oxygen, so 5 is Z. Carbon 3, we have a hydrogen here, which means higher priority is on this side. On the left side, we have higher priority here, the carbon bond to 2 carbons plus oxygen versus bonded to 2 carbons. So we have 3 is E. And then the chiral center over at 2, bromine is highest priority, carbon bonded to oxygen is second, and carbon bonded to carbons is third, makes it R. So again, carboxylic acid nomenclature, almost identical to aldehyde nomenclature. The place where things change for carboxylic acids is when we have diacids. And specifically diacids where the carboxylic acids are at the end of the chain. And I've drawn the first 6 here. And you can see that they just increase by the number of carbons from one drawing to the next. So these are known as oxalic, malonic, succinic, glutaric, adipic acid, and pimelic acid. And a lot of these diacids are actually fairly important molecules biologically. And one of the places we can see that is in the following. So here's our citric acid cycle. And you can see actually almost every compound within the citric acid cycle is an anion of a diacid. In fact, even more specifically down here at the bottom, there's succinate. What is succinate? Succinate is just succinic acid when you've lost the 2 acidic hydrogens. And you can see in other places here we have the 5 carbons, which is a derivative of glutaric acid. So a lot of these diacids play fairly prominent biological roles. Now, how do we remember these names? Well, a long time ago when I took organic chemistry, this was the mnemonic my professor taught me, and it's actually still the mnemonic that I use to remember the diacids many, many years later. Alright, so what are some of the important properties of carboxylic acids? Well, carboxylic acids among organic functional groups have very, very strong attraction, very strong intermolecular forces. And the reason for that is 2 things. So first of all, you've got this highly polarized CH, or a carbonyl bond. In addition to that, the OH group allows for hydrogen bonding. So another way of thinking about it, you take all the best aspects in terms of strength of intermolecular forces that a ketone has, that dipole-dipole interaction, all those strong forces that an alcohol has through hydrogen bonding, and in a carboxylic acid, you end up with both. Or what we often see with carboxylic acids is that two of them can line up like this, and you get two attractions between the molecules. And so it's a relatively strong intermolecular force, strong attraction. And we know, we've done this previously, that we can compare this to other compounds, other functional groups, by looking at boiling points. And what I've done here is I've chosen 4 compounds that have approximately the same molecular weight. They're not exactly, but pretty similar. And so our hydrocarbon down here at the bottom has just van der Waals forces. The aldehyde here, and this could have been an aldehyde or it also could have been a ketone, has dipole-dipole as its dominant attraction. The alcohol has hydrogen bonding. And the acid has both. And so you might expect that of these, the carboxylic acid will have the highest boiling point, and that's exactly what we find. All right. We also like to talk about solubility. And at least initially, same rules apply as with other functional groups. Less than 4 carbons, generally water soluble. But as that number of carbons goes up, generally not that soluble. However, there's one major exception for that. And that's what we're going to deal with in the next section, the next video, when we start talking about acidity of carboxylic acids.